All right, here's a fun one. So we're told steam is compressed by reversible, reversible by a reversible isothermal process from 15 bar 250 degrees C to final state that consists of a vapor-liquid mixture with a quality of 32%. Calculate the amount of work and calculate the amount of heat that's required to maintain isothermal conditions. And is the heat added or removed from the system, right? So it'll just be a matter of determining the sign. So let's do it all at one time. Okay. So let's see. So we have some initial state in which my initial temperature is 250 degrees C, and my initial pressure is 15 bars. Okay, and my final state is, well, we're told we have an isothermal process. So T2 is going to be equal to T1, and that'll be equal to 250 degrees C. And I'm not given a final pressure, but right, we're told that we have a vapor-liquid mixture with a quality of 32%. Right, so I'm at VLE, where Q is equal to, I'm at VLE with a Q of 0.32. So if I have a single component, single phase system, I have 2 degrees of freedom. So my initial system is specified. But if I'm at two-phase coexistence, if I have a single component two-phase system, I have just a single degree of freedom. Right? So the state of my system is fixed just by knowing temperature. All right, so the state of my initial and final state is fixed. And in A, we're asked to calculate the work, and then B, the heat. Now, we're told that we have a reversible isothermal process. So we have a reversible isothermal process. Okay. So based on everything we've done already, I'm already thinking of entropy. All right. So what I'm thinking is our definition of entropy is that ds is equal to dq reversible over t. All right. So ds is equal to dq reversible over t, right? Now, so we're told we have a reversible isothermal process. So what I should have then is that, I'm going to write this as T ds is equal to dq reverse. Okay. Where t is constant. So I'm going to have t times the integral from my initial to final state ds, okay, which is equal to t times S2 minus S1 is equal to Q reversible. All right, so I'm going to box this in. So my state of my initial and final state is known as specified, so I should be able to look up all my properties for my steam tables. So once I know S of my initial and final state, and I know my temperature, right, T is constant, I can calculate my reversible work, or reversible heat, or my heat exchange for the reversible process. And then to get work, well, then I'll go to my first law of balance. So first law of balance is delta U is equal to Q plus W. Okay, or W then is equal to delta U minus Q, where I'll take Q to be my reversible heat exchange, which I just computed. Okay, and delta U, well, that's going to be U2 minus U1 minus Q reversible. All right, and if I wanted to put it all together, W is going to be equal to T times S2 minus S1. Oh, that's my second term. Hang on. Is going to be equal to U2 minus U1 minus T times S2 minus S1. Okay, so this should be my, ideal or reversible work. So what I need to do then is I just need to solve for, or go to my steam tables and look up U1 and S1. And then for 2, right, it's a saturated vapor. And so what I'm going to need to do is I'll need, U2 vapor, U2 liquid. Let me try and write it here. So I need to know U2 vapor, U2 liquid, and I'll need S2 vapor and S2 liquid, where then U2 will be Q times U2 vapor plus 1 minus Q U2 liquid, and S2 will be equal to Q times S2 vapor plus 1 minus Q of S2 liquid. All right, now let's do it. Now, how wonderful would it be if both these data points were in our steam tables, or superheated steam tables and steam tables? I'm hoping. Let's find out. So for my first point, let me go my superheated steam tables, and hopefully 15 bars is on here. 15 bars is on here. That's great. And at 15 bars, my saturation temperature is 198.30 degrees C. My temperature is greater than Tsat at 15 bars, so I have a superheated vapor. So I'll read over at 250 degrees, right? I have U and I have S. So U is 2696. So this is 26. Come on, stylus. 2696. 2696. That's going to be kilojoules. Come on. Kilojoules per kilogram. I need to just not write units. Okay, got it. Okay, and then S. So 2696. S is 6.71111. 6.71111, and that's going to be kilojoules per kilogram Kelvin. Okay, and again, my apologies. I'm blaming it on this new stylus. All right, now T2. Okay, 250 degrees C. Okay, I'm going to go to my saturated steam tables, and hoping 250 is on here. And all right, it's my lucky day. 250 degrees is on here. So let's get U of my liquid, 1080.7. U of my liquid is 1080.7. That's kilojoules per kilogram. U of my vapor is 2601.9, so 2601.9. Okay. Entropy of my vapor and liquid. So entropy of my liquid is 2.7934. 2.7934 and 6.0722. 6.0722. 6.0722. Okay, and this would be kilojoules per kilogram Kelvin, which they are. Kilojoules per kilogram Kelvin. All right, so I should be able to go ahead and compute everything. Okay, one note is temperature. Okay, given temperature in degrees C, I'm going to want to convert that to Kelvin. So for when I use it here to calculate Q, and then it's used in my calculation of W as well. And then we have the same units for S and U, right? And so units of Q is going to be kilojoules per kilogram, and W will be kilojoules per kilogram as well. So let's go over to MATLAB. We'll type everything in and compute. Okay, so this is problem 5. So in state 1, okay, so I'm going to have, first I'm going to have T, so T1 is equal to T2 is equal to T. That's 250 plus 273.15. Convert to Kelvin. So U1 is 2696. S1 is 6.7111. Okay. Then U2, I'm going to have an entry for liquid and vapor for all of these. So U2 liquid is 1080.7. U2 vapor 2601.9. I'll have entropy of my liquid 2.7934. S2 of my vapor would be 6.0722. And then I just need Q, which is 0.32. So to calculate U2, U2 is going to be Q times U of the vapor plus 1 minus Q times U of my liquid. S2 would be Q times S2 of my vapor plus 1 minus Q times S2 of my liquid. So then Q is going to be equal to T, which is in Kelvin, times S2 minus S1, and W is going to be U2 minus U1, and I'm going to do just a minus Q. All right, so let's save this. I'm problem 5 already. So this is in kilo. Let's see, what are my units? My units are going to be kilojoules per kilogram. So U's pretty big. Well, so I guess, this is times 1,000. So Q, I ended up getting Q, my reversible Q, is negative 1.5006 times 10 to the 3. That's kilojoules per kilogram. Okay, so that's negative 1,500.6 kilojoules per kilogram. And W is 372.1314. And that is also kilojoules per kilogram. All right, so now taking a look at the signs. Okay, so keep in mind what we have. So we have a superheated vapor, all right, and we have this isothermal process in which we compress it till it's a two-phase mixture. So we're compressing at constant temperature until we go from superheated vapor to two-phase mixture. And so we see is W is positive, so that means we're doing work on our system. So work's being done on our system. Q is negative, so that means heat's being removed from our system. So work's being done on our system and heat's being removed from our system. Okay, so in terms of is the heat added or removed from the system, heat's being removed and work's being done on our system. All right, cool problem. That's a cool combination of first and second law. I hope that helps.